part of the board never works properly. Okay, so excuse the mess on the right hand side. What this basically says is that a subset of the real numbers is open if and only if it is the union of open intervals. So let's try and prove this. So firstly, let's try and go this way. So begin the proof. Suppose that a subset of the real numbers is open in the Euclidean topology. Well, now for each point in this open set X, in this open set S, we know from the definition that there has to exist an A and a B. Actually, we're going to call them AX and BX for reasons which should become clear later, such that X belongs to the open interval between AX and BX, and that this is going to be a subset of S. So that's just our definition of an open set in the Euclidean topology. Now, the thing here is that, like, every point X in this set kind of is associated with one of those intervals. And so all we have to do now is write that S is equal to the union over all points in S of these open intervals, AX, BX. And surely this is going to give us precisely S, because for any point in S, we're going to have one of these. So for any point X in S, we're going to have one of these open intervals, AX, BX, which contains that point. And also, none of these open intervals have any points outside of S. They're all strictly contained within S. So it must be that the union of all of them is just equal to S. So we've shown that every open subset of the real numbers is the union of open intervals. Okay then, so now let's prove the other side of this argument. We're going to try and show that if the set is the union of open intervals, then it is open in the Euclidean topology. So suppose that S is equal to the union of some intervals. So we'll just suppose that capital A is some set of open intervals, and that our set S is just equal to the union of all of these open intervals which are in A. Okay, so now we want to show that this S is open. So how do we do it? Well, actually it's really straightforward, because I've already claimed that the open sets are the open intervals are open, and we know that the union of a set of open sets is also open, which would imply that S is open. But I didn't actually show you the proof that open intervals are actually open sets. So let me give you the proof of that now. So this is a kind of aside. So I'll put it in a blue box. So the aside is that an open interval, I'll call it C, D with round brackets, is an open set. And the proof is very straightforward. It's just that for any point inside this open set, we have that if we let A equal C and we let B equal D, then we have that X belongs to the open interval A to B, which is contained within CD. And this happens for any X inside this open interval. So this proves that every open interval with finite boundaries is an open set. And so now we can use this fact. Because now we have that each of these things here is an open set. And so this is the union of open sets. And that implies now that this is an open set. That's the end of the proof. Because the union of any collection of open sets is an open set. So now we're going to see one of those examples where we take something which is true for the Euclidean topology and then we're going to generalize it to something which applies to all topological spaces. In particular, we've just shown that every open set in the Euclidean topology can be written as the union of open intervals. So we're going to generalize that idea and create an idea called a basis. So basically, a collection of open subsets is called a basis if every open subset can be written as the union of members of that thing, of that basis. So let's write that a bit more formally. So here we have it. For a topological space, the collection B of open sets is a basis for a topology tau if every open set, every member of tau, is the union of members of B. So this is our definition of a basis. Okay, so let's just look at an example. The example we've just been discussing, which is the collection of all open intervals of real numbers. So we've just shown that every open set can be written as the union of open intervals. So we've essentially just shown that the collection of all open intervals, this thing here, is the basis for the Euclidean topology on the real numbers. So now let's have a look at another important example of a basis on an important topology. So let's x tau be the discrete space. That's the space with the discrete topology. And now we're going to let B equal a set of all singletons. And now we claim that B is a basis for our topological space x tau, our discrete space. Now again, if you pause this, you should be able to think of the proof for this. Actually, I kind of don't think there's any excuse, because it's really a result which I discussed in the last lecture, or at least it follows from it directly. But I'll give you the proof anyway. Basically, the proof of this, pause now and try and find it if you want, but the proof is that if S is an open set, then S is just a generic subset of X, okay? Because remember, in the discrete topology, tau is just equal to the power set. So the open sets are just all the subsets of X, okay? So now all we have to do, since we know that every singleton is an open set, we're going to have that S is going to be equal to the union of all X belonging to S of the singleton set just containing X. So that's quite enough, really, because what we've shown here is that this generic open set here can be written as the union of members of our set B, and that means that B is a basis for our topological space, because every open set can be made by taking the union of elements from that basis, and those elements are open sets in themselves. Okay, so let's have a look at another important way of looking at the basis of a topological space. And this is quite different looking to some of the other examples we've been considering. So here's a proposition. It says that for a non-empty set X, let B be a collection of subsets of X, and we'll assume that X is associated with some topology. And so now we have that B is a basis well, we'll say B is the basis for some topology on X. Excuse me. Let's see if I can draw an X on this Bermuda triangle of writing. Okay, so we've got our X there. Now then, B is a basis for a topology on X if and only if we have two conditions holding. The first condition is that the whole space, the whole set, can be written as the union of all of the basis elements. And the second condition, which is a little bit more involved, says that for all pairs B1 and B2 of the set of basis elements, we are going to have that the intersection of those two basis elements is the union of some elements from the basis set. So what this result is saying is that another statement equivalent to stating that B is a basis for our topology is to say that the whole set X can be written as the union of basis elements, and also that for every pair of basis elements, if we take their intersection, then we can write that as the union of a load of basis sets, a load of basis elements. So let's see if we can prove this, because I think it's quite a useful result. Okay then, so now let's show that the left statement implies the right statement. So in particular, we'll suppose that we have that B is a basis for our topology X, and then we want to show that our other two conditions hold. So firstly, we want to show that X is equal to the union over all basis elements of these basis elements. Now, why is that so? Well, basically, it's just because X is an open set, and by our definition, X is an open set, and every open set can be written as the union of basis elements. So that's one part done. That's the first part. We've proved that assuming that B is a basis for the topology on X implies part 1, we also need to show part 2 is true. Okay, so now we're going to suppose that B is a basis set for our topological space, and we're going to try and imply the other properties. So, in particular, okay, so here's how we imply the first property, and now to imply the second property is slightly more challenging. We have that for any pair of basis elements, B1 and B2, belonging to basis sets, we have that B1 intersection B2 is the union of members of B. Okay, so this is the important bit we have to prove. Why is this the case? Well, the proof is just that B1 and B2 are open sets, and so B1 intersection B2 is an open set. And so it follows that B1 intersection B2 must be either an basis set, or it must be the union of basis sets. So that completes our proof. Of the right-hand side arguments. That is the proof that the thing on the right implies the thing on the left implies the thing on the right. So now we want to try and prove things the other way around. So we're going to try and prove that given statements 1 and 2, we can show that B is a basis for the topology on X. So we're going to suppose that tau is the collection of all subsets of X which are unions of members of B. So remember, we're assuming the things on the right hand side now, and then trying to show that B is actually a basis. So we'll take tau to just be the collection of all subsets which can be made by things of B. And now let's try and show that this actually induces a topology. So firstly, our statement 1 from our proposition is that X is equal to the union over basis elements. And so what that means then is that X must belong to tau, because it is the union of elements from the basis set, capital B. Also, we must have that the empty set belongs to tau, because it is the union of the collection of no members of capital B. So we have that, now we have that condition 1 is satisfied. Remember, we have to satisfy conditions 1, 2 and 3 on tau to make sure that we have a topology. So we can write our set tau like this. We can write it as the set of all ti such that these t's are indexed somehow. So I is just some set of names, maybe the integers, so we have t1, t2, whatever. So these are our members of tau. Now remember that by assumption, every member of tau, everything ti, is the union of members of B. Okay, so what that means then is it means that the union over all of these elements must also be the union of elements from B. Okay, and so that means that this must also be a member of tau. It means that this too must be one of the open sets induced by this basis. So we've just shown that the union of any collection of these members of tau is a member of tau itself. So that's our second condition implied. So let's just recap. We've got condition 1 required for our open sets here, which is that X and the empty set belongs to tau. So that's condition 1. And now we've just got condition 2, which is that the union of members of tau is in tau. Okay. So what this implies now, this implies that this whole expression, let's just circle it. It implies that this is the union of members of our set B. And so that implies that this expression here is in fact a member of tau. And this expression is equal to C comma D, C intersection D. So in fact we've shown that C intersection D is a member of tau, because remember tau is the collection of all things you can get by taking unions of members of B. So that completes the proof, because we've now shown that the intersection of any pair of elements from tau is also a member of tau. I want to show you how powerful the last proposition we just proved is. So to show you that, let's have a look at the plane, which we can write like this, r to the power of 2. So what this means basically is it's equal to the Cartesian product of the set of real numbers with the set of real numbers. In other words, it's equal to the set of all pairs of real numbers. Basically, you can think of the first element in the pair as the x-coordinate and the second element in the pair as the y-coordinate. So this is basically meaning the plane, okay, with Cartesian coordinates. Okay, so we want to show now, so we want to find a basis on the plane. So the claim now is that open rectangles what's an open rectangle? Well, let's say that it's a set of points x and y belonging to the plane such that x is going to belong to some open interval and y is going to belong to some open interval. Okay, so that's what we call an open triangle. So basically something like this. We have here, and then this could be, let's say this is the x coordinate, so this could be A and this could be B. Well, let's say this is the y coordinate, so this could be C and this could be D. Okay, and the element inside here is our open triangle. Right then, well, what we want to show is that the set of all open triangles forms a basis for a topology on the plane. So how do we do that? Well, in fact, it's really easy, just using our last proposition, because all we need to check is that two different things hold. So let's just we'll take our basis set. Maybe I can just move this over here without too much effort. So we'll take the set of all things like this, for different values of A, B, C, and D. We'll take that to be our basis set. So basically we're just saying that Okay, I'm being a bit too complicated here. We'll take this as our basis set. So basically all I'm saying is that we're saying that B is the set of all open triangles. And now we want to show that B is a basis set. Well, it's fairly easy because we just need to show that B satisfies the two conditions from our last proposition. So firstly, we want to have the entire set, which in our case x is equal to plane. We want to show that that's equal to the union of basis elements. So we can do that. It's fairly obvious, isn't it, that the plane is the union of a load of open rectangles. You can cover the plane with open rectangles. Maybe they intersect, but whatever. If you have enough of them, you can cover the whole plane with them. And secondly, we just need to show that. So this is point 1 of our proposition. Point 2 of our proposition is that for any pair B1 and B2 in this set B, we have that the intersection of B1, B2 can be written as the union of elements of B. Okay, I think this is again fairly obvious because of course the intersection of a pair of rectangles is going to be a rectangle. So just simply from those 2 points, we already get that this is a basis for the Euclidean plane. And this argument can be generalized very easily to n-dimensional Euclidean space. Maybe you can look at that as an exercise for yourself. Okay, so here's a really important fact about the bases in topology. We're going to come back to this result again and again, so we'll call it proposition star. And what it says is that well, let x tau be a topological space and now a family of open sets in this topology is a basis for tau, and that holds if and only if we have that for all open sets in a topology and for all points, so for all open sets U and for all points inside such an open set U, there exists a member of the basis, a member of the set capital B, such that we have that X is inside capital B, which is a subset of the open set. Okay, so what does this mean in English? Basically, it means that if you pick an open set and you pick a point in that open set, then you can find a basis element which contains that point and is itself contained within the open set. Think about it in terms of the real line, for example. If you pick any point within an open set of the real line with Euclidean topology, then you can always find a basis point. You can always find a open interval which contains that point and is itself contained within the open set you're discussing. So this result says that that's necessary and sufficient for this subset B of the open sets to be a basis. So it's a pretty important result. Okay then, so now let's start by having a look at the proof of the result in this direction. So we want to show that if B is a subset, if B is a basis, then it has this property that for any point in an open set we can find a basis element which contains that point and is contained within the open set. So how do we do that? Well, we'll just suppose that we have an open set U, and we'll suppose that X is a generic point inside the open set U. Now what we want to do is find a member of our basis, capital B, which contains U. So the important thing to note here is that U itself is equal to the union over, well, let's index our members of our basis. So we'll index them with i's. So the union over all these different i's of bi. So basically what I'm saying here is that, I'll write it in red at the top, I'm saying that the basis here is of the form, it's a settable bi, such that I belongs to its index set. This is quite a useful way of doing things in topology when you're dealing with potentially uncountably infinite sets. Normally you'd index things with integers, but doing it with integers is not sufficient when you have an uncountable set which has a cardinality greater than the integers. So instead we just label each of our basis elements with a particular element from this generic set called capital I. Well, okay then, so we have this result. What does it get us? Well, what it gets us now is that this implies that there must exist an I such that X belongs to little bi, and that is of course contained within U. So that implies the right hand side of our argument. So we've finished half of the proof now. Let's try to prove the converse of this argument. So we're going to suppose that for every open set U, every member of that set is going to be such that there's going to exist a particular element there's going to exist a particular basis element such that X belongs to B, which is a subset of U. Okay, so what we want to show is that every open set is the union of members of our set capital B. So if we let V be any open set, then for any member of this open set, there exists element bx of the basis set capital B, such that x belongs to bx, and bx is bx is going to be a subset of V. So basically, for every element in this open set V, we can find a particular member of the basis set which satisfies our required properties. We call that bx. And now all we have to do is just write that now we have that V is just equal to the union over all x in V of bx. Okay, and so we have that V is the union of members of B, of capital B, and that completes our proof. So another important proposition about bases. So here's the proposition. It says that for a basis B of a topological space x tau, we have that a subset of x is open if and only if there exists an element of the basis such that x is a member of that basis element, and that is a subset of U. And this has to hold for every member x of our set. Okay? So for every member x of our set, there exists a basis element such that x is in the basis element which is contained within the open set. Okay then, so how do we prove it? Proof. Well, let's just let U be any subset of x. And we're going to suppose that for every member of U, there's going to exist an element of B, we'll call it bx, which is such that x belongs to bx, which is going to be a subset of U. And so now what we get now is that U itself is going to be equal to the union over all the little x's over all the points in U of bx. It's this old argument again. So for each point x, there's a basis element which contains x and is contained within U. So we can write U as the union of all of the special basis elements that go around all the points inside it. And so this gives us that U is the union of open sets. because it's for union of basis elements. Basis elements are open sets. Okay, and that means it's open. Okay, so now we've just proved that the statement on the right implies a statement on the left, and also to prove the statement on the left implies a statement on the right, we can just use the last proposition which we just established, which basically states just that. So that completes the proof of this result. We can have different bases which define the same topology. So a good question then is, when do a pair of bases define the same topology? So this is the question which is answered by the following proposition. So let B1 and B2 be basis, well, let's say bases for topologies tau 1 and tau 2. On some non-empty set X. So now we have that these topologies are going to be the same if and only if we have 2 points holding. We have that for every member of the first basis and every member of the second basis, and every element of that basis, there's going to exist an element of the second basis which is going to be such that X is inside this element of the second basis, and that element is contained within the element of the first basis. And kind of symmetrically, the other point that we need is that for all members of the second basis and for all X in that basis, there's going to exist an element of the first basis such that X is an element of that first basis, and that's contained within the element of the second basis. Okay, so that's what we've got. Okay then, so I'm going to leave it as a task for you to prove that last proposition.